All right, let's talk about something you probably do every single day without giving it a second thought. We're going to pull back the curtain on a piece of tech we all take for granted and look at the incredible, hidden engineering that keeps it so unbelievably safe. No, seriously, think about it. Every day, millions of us step into this thing and we just trust it. We put our lives in the hands of this incredible, invisible dance of physics and engineering.
Yup, the elevator. But here's the thing, it is so much more than just a box on a rope. And we know this thanks to some really deep analysis from the engineering specialists over at Navan Puya. They show it's like a symphony where every single part has to play in perfect harmony to keep you safe. So, you ready? Let's start our tour at the very, very top.
Okay, so we're starting way up high, in a place you've probably never seen, the ceiling of the elevator shaft. This one part of the building has a massive job. It has to hold up literally everything, the whole system, plus all the forces that come with it moving. So first, you've got what are called static forces. Think of this as the baseline, the constant, non-stop weight that the ceiling has to support 24/7. It's the pull of gravity on the whole setup, a weight that never, ever goes away, not even when the building is empty at 3 a.m.
And what are we talking about here? Well, it's everything. You've got the weight of the empty car, sure, but then you add the maximum load, all the people or cargo it's designed to carry. Then there's this huge counterweight, and on top of that, you have the steel ropes themselves, which, in a skyscraper, that's a ton of weight. It all adds up to one massive, constant load. But see, that's just the standing still part. That constant weight is only half the picture. The other half is what happens when the elevator moves. We're talking about dynamic forces, those sudden jolts, when it accelerates, when it brakes, or especially during an emergency stop. Those are some serious, unexpected shocks to the system.
So, how in the world do engineers plan for both of these? Well, they use a surprisingly simple but absolutely critical formula. The total force the ceiling has to handle is that static force we just discussed times a safety factor they call K. And that K is what accounts for all those dynamic jolts. And get this is the crazy part. That little K factor, it can go all the way up to 2. What does that mean? It means a sudden emergency stop can literally double the entire load on that ceiling in a split second. So that structure isn't just built to hold the elevator, it's built to hold 2 elevators, just in case.
Okay, so we've been at the ceiling. Now let's travel all the way down. All the way to the very bottom of the shaft, because that's where we find our next unsung hero.
And we're talking about buffers. Now, don't just picture a simple spring. No. These are seriously sophisticated pieces of tech. Their one and only job is to be the absolute last line of defense. If everything else goes wrong, the buffers are there to catch the car or the counterweight and bring it to a safe, controlled stop. They're the ultimate just in case.
How do they work? It's all about energy. They take all that kinetic energy, the energy of a massive object in motion, and they absorb it. They have to be designed so perfectly that they can soak up all the force of a fully loaded elevator car coming down at speed. They turn what would be a disaster into, just a big stop.
Okay, so that leads to a really interesting question, right? If you need this giant shock absorber at the bottom of the shaft, how does that affect the design of the actual building? The answer is pretty cool, and it shows you just how connected everything is. Right, the safe zone. This is where it all clicks together. The design of that one safety feature, the buffer, literally dictates the size and shape of the entire elevator shaft. It carves out these crucial safe spaces. So here's the light bulb moment. How much that buffer needs to squish down to absorb all the energy? Well, that number tells you exactly how deep the pit at the bottom of the shaft needs to be. It makes sense, right? A faster, heavier elevator needs a bigger buffer that compresses more, so it needs a deeper pit. And this pit, this empty space at the very bottom, it's not just wasted real estate. It serves a really, really important purpose for the people who keep these things running. Because here's the thing, that pit has to be deep enough so that even if the elevator came all the way down and completely squashed its buffer, there would still be a safe space for a technician working underneath it. It's a refuge. It's designed to save a life. And believe it or not, the exact same thinking applies at the very top of the shaft. That space up there, the overhead clearance, isn't just random. It's also calculated based on those buffers down in the pit. Check this out. It's designed so that if the counterweight went all the way down and hit its buffer, the elevator car at the top of its journey would still have plenty of room. It guarantees the car can never, ever hit the ceiling. It's another one of those perfectly calculated safe zones, protecting you and protecting the machine.
So all of this really brings us to the main point of this whole thing. We've talked about the ceiling, the buffers, the pit, but the real magic isn't in the individual parts. It's how they all work together. It's this idea of integrated safety engineering.
The takeaway here is that nothing works in a vacuum. The forces on the ceiling decide how strong it has to be. The design of the buffer decides how much energy it can absorb, and how much that buffer compresses decides how big the pit and the overhead have to be. See? It's like a perfect domino effect, a chain where every single link is absolutely critical.
And this whole concept is summed up perfectly in that Noven-Puya analysis we mentioned earlier. It's not just a box of parts that happen to work together. No, it's designed from the ground up as a single harmonious system, where every piece is integrated for one purpose: safety. So next time you step into an elevator, just remember, you're not getting into a simple box. You're stepping into the middle of a symphony of safety, a precise, calculated performance balancing immense force, incredible energy, and physical space, all of it working together behind the walls just to keep you safe.
Kind of makes you look at the world a little differently, doesn't it? What other hidden engineering symphonies are playing out all around us every single day? All these complex systems working perfectly in the background, just keeping things running. Definitely something to think about. Thanks so much for joining me.